This is the second of a 7-video series on hypothesis testing, one proportion. Here's a claim about a proportion. Suppose we wanted to prove that more than 15% of Americans smoke cigarettes. And suppose we wanted to test this claim with a significance of 5%. What does this mean? What it means is that we're willing to accept up to a 5% chance of getting a false positive. Now, let me explain what I mean by false positive in a statistical sense. It's also known as a type 1 error. I'll call it a false positive. Suppose we went out and did a survey and 19% of the respondents said that they smoked. Would that prove that more than 15% of Americans smoke? Well, it might be evidence in that direction, but it wouldn't prove it because just because 19% of our sample smoked doesn't mean that more than 15% of all Americans do, because after all, samples vary. So it's always possible that you can get a false positive by getting sample data that appears to support your claim, but the only reason you got the sample data that you did was by chance. Now, when we say we want to test the claim with a 5% significance, we're saying we're willing to accept up to a 5% chance of a false positive and still claim that there's enough evidence to support what it is we're trying to prove. So here's the sample data that we collect. We survey 200 people, 35 of them smoke cigarettes. By the way, 35 divided by 200 is 17.5%. And this does appear on first glance to lend evidence to the claim that the percentage of smokers nationwide is more than 15. Notice that this is 2.5% higher than the number in the claim. More on that later. Now, out of the 5-step hypothesis testing sequence, the first 2 are usually done for you if you're a student in a statistics class. In other words, if you're in a stats class and your professor's giving you a problem, there's probably already a claim and a significance in there, and the random sampling has already been done, whether that means that the professor actually did random sampling or whether it means that they just made up some numbers to act as a random sample. But we're going to jump into step 3 here, which is really the first thing you do as a student, is you assume a mindset of equality, and I'll show you what I mean by that. Notice the claim in green that more than 15% of Americans smoke. We're going to assume equality instead, that it's not more than, but what mathematics would we be able to infer from this if the proportion of smokers was exactly 15%? Now, we don't have any reason to assume this. We don't have any proof of it. But what we're going to do is we're going to assume that the proportion is exactly 15%. Why would we do this? Because if we assume that it's exactly 15%, and we can calculate that the 17.5% sample that we got is a rare event, then we can follow the logic that we made an assumption, we found a rare event, and therefore the assumption may have been false in the first place. This assumption, contrary to what we're trying to claim, is statistically called the Null Hypothesis, whereas the statement we are trying to find evidence for is called the Alternative Hypothesis. But putting aside the names, let's get to the actual mathematics. So we're in the mindset of equality here. We're assuming that exactly 15% of Americans smoke, and we're assuming this for calculation purposes. Let's imagine what a sampling distribution would look like in that case. Here's a sampling distribution of p hat, and when I say p hat here, I don't mean the 17.5% specifically that we got in our sample. Remember, a sampling distribution is a curve that shows what many repeated samples of 200 people might look like. In other words, if we sampled 200 people over and over and over, and each time computed the sample proportion of smokers, we would get most of the results near 15%, at least if 15% of Americans smoked. And the further we got away from 15, the less results in that range we would have. So that's the idea of a sampling distribution. Now, what about this 17.5%? What this problem really comes down to, because that is higher than 15, but this what it comes down to is that 17.5% near 15, so that it wouldn't be that rare to get a sample that high, or is that 17.5% much further away from 15 to the point where we wouldn't expect a sample that high given the null hypothesis? Because if that's the case, then we can cast a shadow of doubt on the null hypothesis, and that lends favor to our own claim that more than 15% of Americans smoke. So, step 4, which is really the second step for a statistics student, we have to find the probability that a sample can be this far away if the null hypothesis is true, that 15% of Americans smoke. Now, in order to compute this probability, we need something called standard error, a test statistic, which is really the number of standard errors that our sample data is away from expectation. And we're going to use the normal distribution to compute the probability that our sample is that far away. Essentially, these are the formulas you'll need, so let's go through them in this case. First, our standard error. Notice I got 15% from the assumed percent of smokers, 85% from the percentage of people who don't smoke under our assumption, and 200, you'll notice, is my sample size. So the standard error in this case turns out to be about 1%. Well, what does that mean? Well, that gives us a way to compute our test statistic, which is the number of standard errors. In other words, that 2.5% discrepancy between the null hypothesis and the sample proportion, how many standard errors is that? Well, to find out, I would just divide 2.5% by the size of a standard error. Or if you prefer, use the formula shown in the table for z. Either way, we have a z-value, or a number of standard errors, of about 2.1. Well, what that means is that my sample data is over 2 standard errors away from the assumed population proportion of 15%. And whenever something's 2 standard errors away from the mean, that's a pretty rare event. To find out how rare, we use normal CDF in your Texas Instruments graphing calculator or other software. And you'll recall from previous lessons, I'm assuming, depending on where you are in statistics, that normal CDF is a feature that tells us the probability of an event that far away from the mean. In this case, I got a what's called our p-value. Our normal CDF gives us 0.016. What does that mean? That means that if the null hypothesis were true, and that exactly 15% of Americans smoked, the chance of me getting a sample this high, meaning 17.5%, is only 1.6%. In other words, based on the null hypothesis being true, the sample data that we collected represents a very rare sample. So now I'm ready to state my conclusion. Remember, we were going to test this claim with a significance of 5%. That meant we were willing to accept up to a 5% probability of a false positive. But what this p-value shows us is that my sample is so rare that it represents only a 1.6% chance of a false positive. And my final conclusion, therefore, is that there is sufficient evidence to support the claim that more than 15% of Americans smoke cigarettes. Let's look at a second problem. Suppose a recent article showed that 56% of people own stock, and we want to claim that that article is incorrect. So we've read an article, it states 56%, and we want to dispute that article. And we want to test our claim, again with a significance of 5%. Claim significance percentages are not always 5, but it's a good number to use for my first two examples here. What does this mean? Again, it means if we find out that there's less than 5% chance of a false positive, we're going to assume that our claim has been supported by the evidence. So we do some sampling. 400 people surveyed, 206 out of those 400 own stock. 206 divided by 400 gives me a 51.5% sample proportion for those who own stock. Well, let's see. The article claimed that 56% of Americans or people own stock, and I have a sample where only 51.5% of them own stock. Does that mean that the 56% is wrong? Not necessarily, because it's possible in a world where 56% of people own stock that a sample could be as low as 51. The real question is, how likely is that? Notice, by the way, that this is 4.5% below the number claimed in the article. So let's go through our 5-step process again. Again, the first 2 steps you would be unlikely to do as a student of statistics in a classroom. Steps 1 and 2 would be done for you. They'd be stated in the problem. Here's a claim, here's the significance. The problem would go on to state that some data had been gathered, present you with that data, and we're going to jump into step 3, which for you would be step 1 more than likely. Assume a mindset of equality. So if we think the article is wrong about 50%, we're going to assume to the contrary that it's right, and that exactly 56% of people own stocks. Why do we do this? Well, if I can show that my 51.5% sample proportion is far enough away from 56, then I'm going to come to the conclusion that my null hypothesis, this thing that you see in red, was probably wrong. And that would support my claim in green that the article is incorrect. Reminding you of the statistical names of the 2 statements. Now let's imagine a sampling distribution in a world where exactly 56% of people own stocks. What would p-hat values look like? Well, most of them would be near 56%. But it's possible that because samples vary, it could be lower or higher than that. Now, if my 51.5% ends up here, then that won't be far enough away from 56% for me to call that statistically significant. But if 51.5% is much further away from 56, so far away as to be in one of these red tails, then I'll claim it as a rare event and assume that the null hypothesis is incorrect or unlikely. Now notice in this problem, I have 2 tails drawn in red. And you may recall in the previous problem there was only 1. Notice in the claim that the article is incorrect. The claim did not say that the article was too high, nor that the article was too low. It simply said it was wrong. So if I get any sample data that's much higher than 56% or much lower than 56%, either direction, I will consider that as evidence that the 56% stated in the article is incorrect. So here's the big step, the second thing we do, or step 4 overall, where we do the actual calculations. Well, we have the same formulas as before, since we're doing a claim about one proportion. we compute all the stuff the same way. Notice 56% is the claimed proportion of stock owners. 44% would be the proportion of people who don't own stock. And I have a sample size of 400. This works out to about 2.5% as a standard error. Now my test statistic is my next calculation. My test statistic is the number of standard errors that my sample data is away from the mean. Well, remember, my sample data was 4.5% away, in this case 4.5% below the suspected mean of 56%. So I'm going to divide that by the size of a standard error to find out how many standard errors my sample data is away from the mean. If that logic escapes you, then you can see there's a formula for it above. So I'm going to use the normal distribution now to find out the probability that my sample data would be that far away from the mean. And what I have here is a probability value of about 3.5%. But this is what we call a two-sided claim. In other words, we're claiming that something isn't 56%. But we're not saying it's higher or lower. So if I were to get evidence either way, either above or below 56% by a statistical significant amount, that would essentially lend evidence to my claim. In other words, because I haven't specified whether I expect the sample proportion to be much higher or much lower than 56%, I have to double my p-value in this case. In other words, 3.5% doubled is 7%. And here's the logic. If there is a 3.5% chance that my sample statistic was as low as 51.5%, then there's an equal 3.5% chance that it could have been that far above. And since either one would have counted as evidence against the article, we have to double the value of p and compare that to the significance of the claim. Now that's a little bit strange in logic, and if the logic escaped you there, just remember this. If your claim is not stating that something is above or below a certain number, simply that it isn't that number, just get in the habit of computing your p-value and doubling it and comparing that. Now, to state the conclusion, let's remember that we were testing this claim with a 5% significance, but there is a 7% chance, counting below or above 56, that my sample data could have been that extreme. And I did not get a probability value lower than the significance. And since that value of 7% is more than 5%, my original significance claimed in the problem, then I don't have enough evidence to support the claim that the article is wrong. Now, might the article be wrong? Certainly. But the sample proportion of 51.5% wasn't far enough away from 56 for there to be evidence to support the claim. So I'm not saying the claim is wrong. We don't know. What I am saying is there isn't enough evidence to support the claim. And that completes video 2 of 7.